Good afternoon, everybody. This is Steve Wilson at the Illinois State Water Survey. Um, Today, our webinar is entitled Groundwater and Well Construction 101. Thanks for joining us. The State Water Survey is at the University of Illinois. We've been around since 1895. We house the state's well logs. We also provide pump tests and other kinds of services to communities in Illinois. And it's the home of the private well class, which is funded by the EPA through a grant to the Rural Community Assistance Partnership. And so we partner with RCAP, and I'll talk more about them in a second. They have folks in every state that are technical assistance providers and work with well owners and small communities, water and wastewater operators all over the country. Again, thanks for joining us. Let's see here. There we go. So today's webinar is part of our program, the Private Well Class, and it's also part of this national private well program that RCAP manages. We're one of the partners on RCAP's grant, along with other notable groups like the National Groundwater Association, the Water Systems Council, and the National Environmental Health Association. So the materials today are going to follow what's in the private well class, but this is not the class. It's a webinar to go over some of the material on a given topic, as well as allow you to participate and ask questions. And so I do want to make a point that if you haven't signed up for the class, it's free. You sign up on our website, privatewellclass.org. You sign up through your email, and it sends you a PDF once a week for 10 weeks. You're on your own to read it and follow through with it. But it's much more comprehensive than we can cover in our 2 hours today. We do record all of our webinars, so like this webinar is being recorded today. It will eventually show up on our YouTube page, along with all the other webinars we've done over the last 6 years. And so the neat thing about these webinars is, as you noticed when you registered, you're taken to a page where you could ask questions in advance. We've got, I think, a little over 80 or 90 questions today. We'll answer 15 or so of those at the end. And so it's a chance for you to participate and get your questions answered, as well as if you didn't ask a question or your question doesn't get answered as part of the slide deck today, at the very end, we'll stay on and answer questions for as long as you like. And so to facilitate that, we ask that if you have a question as we're going through, or your question doesn't get asked and it's not on the slide deck as we're near the end, you can put your question in the question box or chat box, and we will add it to a list and we'll go over those at the very end. Yeah, so we also are a CE provider, continuing education provider for NEHA and for Illinois LEHP credit. And so if you're an environmental health professional looking for CEs today, the thing to note is like NEHA has a 2-year credentialing cycle. If your cycle just started and you take this class today, you won't be able to take it again for 2 years. And so we've listed down at the bottom right the times we've hosted this class with the same core content over the last 2 years. And so if you got credit for it back in May or in last December, then you can't get credit for it again. What we provide is a copy of the slide deck, completed forms for NEHA, and a certificate of attendance. This is our email address. We'll reach back out to you with that information once we're done with the webinar, and we can show that you've been here the entire time and paid attention and all those things. Now, there are some groups that allow their members or their professionals to use our webinars for continuing education credit. A few drillers, state agencies do for their drillers. And so if you're just looking for a certificate and the slide deck, just email us and let us know, and we can do that. So I'm Steve Wilson. I'm a groundwater hydrologist at the State Water Survey, and I'll be doing all the speaking today. Katie Buckley is also here. She's our outreach specialist, and she's fielding questions during the webinar that are in the chat box or the question box, and those that we need to answer at the end will go on a shared document that I'll pull up at the end. And then she also will handle all the CE work related after the webinar. And also I want to mention Walt Kelly, who's the head of our groundwater section. He's a geochemist, and he helped answer some of the questions that you all asked in advance that we have in the slide deck. Okay, so a little bit about RCAP, the Rural Community Assistance Partnership. It's made up of 6 regional nonprofits. You might know them depending on what state you're in. If you're in Texas, it's Communities Unlimited. If you're in California, it's RCAC. Each of those 6 regions have staff that are private well experts, and we work with them directly. And so if you are a professional and you want to put on a workshop for well owners in your area, we can get you in contact with an RCAP person that represents your state. They're glad to work with you. They'll help. They can find speakers. They can do the legwork. Whatever you need, they're willing to partner and work with you to reach out to more well owners. One of the neat things that RCAP does is back in 2016, I think we developed an assessment tool to use when visiting with a private well owner on their property. They provide that as a service. It's free to any well owner. And so a lot of times they get asked by a county health department or a local health district or even a state health department to go visit with a well owner that might have some kind of problem. And it's an assessment of everything related to the well. I only have this one front page of it, but it's got 18 sections in the end, and it's really comprehensive. Talks about everything from their septic to treatment, type of pipes in their home. It's a site visit. They look for the log if there's a geologic log available, anything else that might be available in the state records related to that site. And they provide all of that information, including pictures at the end, to the well owner, along with recommendations on best practices they might want to follow, especially for anything that's found that could be a vulnerability or a risk for their well. And again, let us know. You can contact us, and I can get you in contact with the appropriate RCAP person, depending on where you live. So, and these assessments are kind of like if you're with the health department that does sanitary surveys for community water supplies, it's basically like a sanitary survey. It's a way to educate well owners as well as go through, all the things that they need to be concerned about. Again, looking at the type of pipes in their home, if it's an older home with lead pipes, all those sorts of things. Gives you a chance to promote best practices, and it also encourages communication and that sort of thing. So enough about RCAP. Before I talk about, they've done over 3,000 of these already, as well as workshops around the country. We've held a number of workshops to teach people how to use the assessment tool, and through that we've developed relationships with several hundred partners, basically labs, hydrologists, county health or local health districts, all those sorts of folks. So it's really a worthwhile thing, and I can explain that more to anyone who's interested. Just let me know. So before we talk about the State Water Survey, I almost forgot. Katie wants to do a poll, and or I want to do a poll too. So Katie, why don't you go ahead and launch that? Again, just to make sure everybody's paying attention.
Sure thing. I'm launching it right now. We just want to know what role best describes you today on our webinar. So go ahead and feel free to select your answer. Give it a few more seconds.
Yeah, we really appreciate everyone filling this out. It helps us. We need some of these things. Because our funding comes from US EPA, they're curious about what percentage of the folks we're actually reaching, as well as like if you take our private well class and sign up for it, you'll see that it asks for 3 things: your email address, your first name, and what state you live in. And that's also so that we can demonstrate that our class is reaching people all over the country. And in fact, we've had people from probably 12 or 15 countries outside of the US who've taken our class as well. So 85% have voted. If the other 15% could vote, that'd be great.
Give it a few more seconds and then I'll close the poll.
We do use this when we're deciding on CEUs to make sure people are paying attention.
All right, we have 87%. I can close it, Steve?
That's fine.
All right. Would you like me to share the results or no?
That's fine. Yeah.
All right. looks like most of you guys are from a regulatory agency on here today. All right. All right, you're good, Steve.
All right, so the water survey was founded in 1895 because of cholera and typhoid outbreaks. And formed by our state legislature, we were one of the scientific surveys, like a state geological survey or natural history survey. Illinois just has a water survey in addition. We have a groundwater section and an environmental public health section here, which I lead. And we do a lot of applied research as well as public service and outreach. And like I said, we've been around since 1895, and we house the state's well logs, including all the records for community water supplies since their inception, or since 1895, whichever came first. And so because of that, we've got a ton of really cool records and information in our files dating back to pre-1900 about, this is a glass plate slide. You can see the slide up at the top. It's broken, but it's in our archives, and it's they were trying to determine where typhoid was coming from, and so they in Rockford, Illinois, in 1913, and so they followed this E. Erickson on his dairy route to see which of his patrons actually were cases, and it turned out it looks like 8 of those were out of the 112 that as of by September 10th. Just really cool stuff. That's the work we did back then. You know, we still do some of these types of projects. We're actually sampling some wells in Illinois for Legionella and lead, and 2 separate projects, trying to get a handle on what kind of risks those might be for private well owners. Yeah, just if you're a driller, you can really appreciate the work that goes into installing a well back in, you know, this is in 1935, I think. All the welding and the rivets that had to go into that, where now it's all threaded casing, and the spacer bars there. This is every 10 foot they put in, you know, I don't know how many rivets that would be, but it's a bunch. And so it's just amazing where we've come in that time. And so it's just cool to share the way the groundwater and well world was and is today. And you know, this is putting a well in for Weldon, Illinois, which is a small community in central Illinois. And off to the right is an engine, steam engine, powering all this, but it was a lot less safe and a lot more work to put in a well for even a private well or for a small community back in the day. So what we're here to talk about today, though, are private wells. So private wells aren't regulated after they're constructed in general in the country. And there are a few local health districts in the Northeast where they may have some more authority after the wells are installed, or when there's a property transfer. But in general, it's up to the owner and user of the well to be sure your water's safe and the system's maintained. Where for a community water supply, even a community that's on groundwater, like Champaign-Urbana is on a groundwater supply, we have a water system. And for us, it's Illinois American Water that ensure water's safe to drink. They test it, they keep the pipes safe, updated and maintained. They have a licensed operator who runs the system and does the treatment. And so when we turn on our tap, we always have water. As a private well owner, that's you, and you're in charge of it. So, and the other thing to remember is, you know, a lot of people swear by their groundwater or their well water. It can be the best tasting and safest in the world, but it also can have contaminants that are colorless, odorless, or have no taste. And the one I use most of the time for an example is arsenic. I've done a lot of arsenic research in my time here, and it has no taste, odor, or color. And you won't know you have it in your water unless you test. And that's the message, is that you need to test your well regularly. So now I pay $40 or $50 a month for my water every month. And that's spread out over the 150,000 residents, 180,000 actually. But you need to do that for yourself. I grew up on a shallow dug well on a farm in central Illinois. And, you know, we had all kinds of problems. If it was a dry summer and we left a hose on in the horse tank, we'd run out of water, or in the winter, if our power went out, our pipes might freeze because our pump was above the well, not buried in the ground. And so there's just a lot of responsibilities if you're a well owner that you need to know and understand. These are some of the big takeaways, if you will. You need to understand your well log or your well, how deep it is, where the pump's set, if it has a screen or not. What type of well is it? Where's your water coming from? Is it coming from near the surface, or is it coming from fairly deep? And well depth doesn't necessarily give you that answer, which I'll go through in a little bit. You can have a really deep well that's still getting water from shallow formation. So you need to understand those things. As far as understanding if there are natural occurring contaminants with your water source, there's your state agency or maybe even your local health district or county health department will know. So for instance, we know there's areas in Illinois that are high in arsenic. Tazewell County is one of those. If you called the Tazewell County Health Department, they would recommend you test for arsenic, just because we know there's a lot of it in that particular aquifer that folks are using. So the other point of our class, though, is to teach you enough about the basics related to your well and how it works and the geology and how contaminants can get into a well, that you learn to ask better questions and the right questions and understand what your local sources of information might be, whether it's a driller, extension, a county health, a lab, or a state agency like your state geological survey or your USGS office, or in Illinois, the water survey. All those things, the more you learn about your well and talk to folks who are interested in helping you, the better off you'll be. And lastly, and I'll mention this a bunch of times probably today, is sample your well. And we recommend sampling annually for nitrate and coliform, and every 3 to 5 years for a set of inorganics and metals, just so you have a better idea of the chemistry and understand that nothing's changed with your well and that it's safe to drink. So we're going to do a little bit of a geology lesson to start out today. This is about groundwater and wells. So porosity is one of the major terms used in describing how much water there is in a system, in a groundwater system, an aquifer, as well as how it might move through that system. So if you had a box like this one full of sand, the porosity is the volume of pore space, which is the area between the sand grains divided by the total volume. So the best way to explain it is, if I have a jar of sand that is full of fine sand, it might look like it's completely full of sand, but it actually has a porosity of nearly 30% if it's uniform sand, which means if I have a 100-foot thick aquifer of uniform sand and it's full of water, if I took all the sand away, there'd still be 30 feet of water there. So a sand and gravel aquifer that's porous like that typically is a very good water supply if it's very thick and it's completely saturated. And it also depends on the size of the grains, how easy it is for water to move through that material. So that's a sand system. A bedrock system, a fractured rock system is what this is basically water doesn't come. If I have a piece of granite in my hand, it has zero porosity, right? It's not the rock that's providing the water or storing water, it's the fractures in the rock. Now, one type of bedrock, especially sandstone, can have secondary porosity. You can have water stored in sandstone. It's not very much, but it provides a little more. It's basically cemented sand. But in general, water flow in bedrock aquifers is through the fractures. And so you'll see when we get to the part about how bedrock wells are built, that really matters. And it's why, when you can't have a casing all the way down to the bottom with a bedrock system, because then the fractures get cut off as well. Okay, so unconsolidated is a term meaning loose, like sand and gravel, and consolidated is rock, okay? And so usually there's some unconsolidated material, like the 2 feet of good earth material that might be on top of the soil. If it's a sand and gravel aquifer, you can see there's a well-sorted sand and a poorly sorted sand listed here, and you can see the amount of water in there. That's misleading, because usually a well-sorted sand will have a higher porosity and hold more water than a poorly sorted sand, where those smaller grains can fit in between the bigger ones. And in a rock system, it shows fractured rock on the left, fractures in granite, which granite, like it's the basement, if you will, of all bedrock on the earth. is usually very hard and very small fractures. So if you have a well that's in granite, and I probably will talk about that at some point today, somebody in Colorado that's on a mountainside, you are lucky if you even hit a fracture and have any water. You can drill a hole that's completely dry if you miss all the fractures. Versus caverns in limestone. We have a lot of limestone in Southern Illinois, Indiana, Tennessee, Kentucky. It's where Mammoth Cave is. That's the limestone is more it's more friable as far as it can be dissolved by water, and so that's why you have sinkholes and karst aquifers. You hear about that sometimes. That's usually limestone that's been weathered, and that's how caves are formed, and some of those are full of water, and so that makes them more interconnected and larger. But it also means that when you have a sinkhole at the surface, it's going straight down into that cavern, and it's causing contamination. So we see, for instance, Pike County, Illinois is all karst. It's all this limestone that's got a lot of sinkholes. Nearly every sample the county health department does ends up being positive for E. coli or coliform. There's no way around keeping surface contamination from getting in the system, and that's just the way it is. So as far as permeability you can look at it like, so there's two things I mentioned. Porosity is basically the pore space, so that's the amount of volume a given unit of material can hold. And so like for gravel, or sand, it could be up to 30% porosity. The other measure is permeability, and that's kind of the velocity that water can move through this unit of material. So you can see gravel, because the grains are so large, it's very permeable. Water can flow depending on, and water flows based on pressure, right? If I pour water on one end of a table and then lift that end up, water flows down the table. It's trying to go to a lower place and it wants to be level. And so it flows based on pressure. So if one part of the aquifer has a higher water level than the other, water is moving from the higher elevation to the lower one, and that's what drives the water flow in an aquifer. And an aquifer is part of the hydrologic cycle. The water that's in there today may have been somewhere else a million years ago or 10,000 years ago, depending on how deep it is. But water is constantly moving and discharging, and wherever there's recharge into an aquifer, somewhere else there's discharge out back to the surface. And so that's why we have, so for gravel, they're very large particles. Water can flow through it really easily, and so it can move as much as 300 to 3,000 feet a day. And then as the grains get smaller, it slows that down a little bit. So sand's still very permeable. It makes up a lot of our sand and gravel aquifers. But then as we start getting into smaller, really small particles that can impede the flow, and you can see for a silt or a clay, it can be, if it's a very tight clay, it can be 1 foot in 10,000 years. And the interesting thing is this clay that's on the bottom left may still have a porosity of close to 30%. It's just that the water can't move through it very fast because the grains are so small. And so it will move through it, but very, very slowly. And then on the right side, the rock side, we have limestone that can be very permeable depending on how big the fractures are. And again, sandstone, same. It can provide a lot of water. Again, you're still dependent on fractures. And then shale is like a cemented clay. So it's typically very low. It's considered an aquitard, like silt and clay are, which means it retards flow, or an aquiclude, which means it prevents flow. So if you have in bedrock, you have layers. You could have a limestone, then a shale, then a sandstone, and then another shale. There's various units. The farther down you go, those shales typically prevent water from moving between any other aquifers that are on each side of it. And so in that case, you could have very different characteristics of chemistry, water chemistry, or even water level could be very different on one side of above the shale versus below the shale if there's aquifers on each side. And then, and so again, you're dependent on fractures, and this just gives you a range of how fast water can move through a system, just to give you an idea. So this is just the way I usually explain this is consider this as a horse trough full of each material, and you poured water evenly across the top. So the sand and gravel, it's got a wetting front, it's moving down through the sand. As you keep pouring water in, it's going to move fairly uniformly and fill that up. Where if you're in rock, again, those are in dolomite on the upper right, those are the fractures. Water's moving down through the fractures because of gravity. On the bottom left is crystalline rock, like granite. Very small fractures, very isolated. If you're trying to drill a well through there, you could miss anything that has water, or you might have a fracture that's fairly large and get lucky. But in real life, there's layers in bedrock. So sandstone and dolomite this shows, and this is still an idealized representation. Most geologic units in bedrock are not flat, they're angled one way or another, and they're not uniform thickness. They can be very thick in some places and very thin in others. And so that's why when you drill one well in an area and you hit 40 feet of sand and there's plenty of water, you could drill a mile away and there's no sand. Just the geology can change that fast. So here's an idealized representation of it all put together. So you have some wells up by the surface. At the very top, that's a river with a sand and gravel and a well around it. So you can see how small the river is on this diagram, and then the sand and gravel aquifer is where the river used to flow when glaciers were melting in the US, several 100,000 years ago. And then all those river valleys filled with sand. If you may not be familiar with it, but down by St. Louis, Missouri, that's the Mississippi. There's a moraine or a drop off about 8 miles from St. Louis in Illinois. As you're driving towards St. Louis, you drop off nearly 200 feet. And that's where the ancient Mississippi bank used to be when the glaciers were melting. So it was 8 to 10 miles wide, and now it's less than a mile wide. And you can see that any river bottom, as you're driving through, you can see where there was you come down into the bottom ground of the lowlands around the river, that used to be all full of water and flowing. And so when all that melting stopped, it filled with sand. That's why you have the glacial drift. If you're in an area where you have a significant glacial component, and those pockets of sand are available as a water supply. And then once you get down to bedrock, you can have limestone, shale, sandstone, all different material. And depending on water quality and the availability of water, you may stop in that first limestone, or you may drill down and get into the sandstone, because either limestone provides enough water. But you can see in this case, the water level in the deep well comes up above the sandstone into the middle of the shale. It's not flowing out of the top of the well, but it's still under pressure, and that's called an artesian well, because the water level came up above the top of the actual geologic unit, the sandstone in this case. So the shale again acts as a confining layer, and that's why water levels do what they like to do. I apologize for how shaded this is. We need to develop a new diagram here. But what this is really meant to show is, there's recharge areas and discharge. This is part of the hydrologic cycle. And so where you have a recharge area, there's a water table up on the left. As it rains and infiltrates in, eventually that makes it into the aquitard, or down, which, very slowly it can move to a seep and then run off to a stream, or it may make its way down into an aquifer, the confined aquifer that looks like the concrete blocks. And then eventually that's going to flow and reach the stream. It says centuries there. So it goes from days to decades to centuries to millennia. So we can date groundwater, and in some cases we see, for instance, tritium dating. You only see tritium where there's been recharge from the surface in the last 70 years, because it's based on when the atomic bombs were dropped and it put tritium in the atmosphere. And so if you sample for that and there's no tritium, you know that the groundwater is more than 70 years old. It's been in there a long time. And there's other ways to date that, and we find that water is 10,000 years old, or whatever it might be. And so that is an indicator of how fast the water is moving through that system. But even the lower aquifer in this diagram where it says millennia, that water is moving to the left. It's still flowing towards some place where it discharges. It's just deep enough that it takes a long time for that to occur. But it is always moving. It's not just sitting underground stagnant, if you will. And so that's why if you have some kind of water quality problem in a well, if it's in the aquifer itself, like arsenic can be, it's natural occurring, you can't just treat your well and expect it to be okay. And that's a bad example because you don't treat the well, you treat the water. But it's always flowing. So more and water's flowing towards your well. And then when you pump it, you lower the water level and that causes more water to flow to the well. Okay, so as far as aquifers and wells, there's really three types of wells. And the way we look at this, there's Duggar bored wells, which are large diameter, and typically those go in where there is no real aquifer. So you don't have sand and gravel that makes up an aquifer, or you don't have bedrock that's either has enough water or has water of a quality that you can use. An example of that, in Southern Illinois, we have bedrock that's maybe 300 feet below land surface, and where there's plenty of water, but it's all salt water from an ancient lake. And so the TDS is like 10,000. So I mean, it's salt water like ocean water. And so it's expensive to treat. It's just really not used as a water supply. And so in the southern third of Illinois, there are two major lakes that provide water to 15 or so counties and all the public water supplies. And for the private well owners, they either have a Duggar bored well, shallow well, if they've got enough, if there's enough material there to have a water table above bedrock, or they have a different source, a cistern, or they haul water, or there's a lot of rural water districts that have developed in southern Illinois because there's no good water source. And so in some cases, you may have more than one choice. In Champaign County, where I'm at, we have sand and gravel and bedrock. No one really drills to the bedrock because we have a very prolific sand and gravel aquifer called the Mahomet. But you could, and in other places you don't have choices, and some places there's just no water available, and that's the way it is. And you as a well owner need to understand where you live, what your choices are, what those differences are. For instance, you may choose, I guess a good example is in Wisconsin, there's one geologic unit that has very high arsenic in the thousands, where the health standard's 10. So they passed a law that says you have to stay above that unit, or if you're going to drill through it, you can't finish a well in it. And if you're going to drill through it, you have to case it off so there's no chance that water from that unit can get in your well. So there's better water below and there's better water above, but this one unit is just very high in arsenic just because of the source grain material that make up the aquifer. And so, it just depends on where you live, as a bottom line. So dug and bored wells, so the well in the upper left here is a hand dug well. It's that's the farm up over on the over the top right. In this case, it's 4 or 5 foot diameter. It's brick lined. They've covered it with a bunch of 2x10s and then put tin over top of it with rocks and concrete blocks holding it. The mud on the far right side next to the post is from cattle. This is a pasture, and the posts are all worn down because the cattle come over and scratch using those posts, as well as doing their business there. And so you can imagine this is a very shallow well. I think it was 17 feet deep. So anything from the surface is going to infiltrate into the ground there and eventually make its way into the well. Very unsafe, very poor water supply. But there's obviously nothing up by the house, which is why this well is down where it's at. But that's a field up above it, up gradient as well. So not only is there cattle here, but there's also nitrate and maybe pesticides that are put on the field certain years. There's a lot of these old wells still in use, and they're hand dug in most cases. The other two wells, well, the well on the right is a 3 foot diameter bored well where you use concrete tile, 4 foot sections vertically, and you set the pieces of tile on top of each other. So where the seams are between those two pieces of tile, it's not cemented and water can seep in. And so the issue here is if that last piece of tile at the surface is a foot above land surface, that means there's a seam at 3 feet below land surface, still pretty close to the surface. And in a heavy rain, if there's any standing water, it's going to infiltrate in, and if you're applying anything to your grass there or whatever, it can get in your well. Versus the well on the bottom left is also a large diameter well, but it has a riser pipe. So this concrete pad that you see on the left is 10 feet below land surface in the other example. And then there's an opening for that pipe, and you're able to fill that all in with clay and reduce the amount of opportunity for shallow infiltration to get in the well. And here's a better example. So the one on the left here was the picture with the concrete pad on the right. You can see the 4-foot sections of tile where there's a seam, there's a male and a female end, and they just sit on each other, and so that water can seep in through those cracks. Now in this example, which is a best practice, they've got concrete for the first 10 feet around the well. That way nothing can get in. And then below that it's open. And so there's no real aquifer here. There's a few little thin sand lenses in the geologic material. And so that allows water to seep in. You drill the hole larger than the casing. So this is a 36-inch casing, and it was probably a 48-inch well, or maybe bigger, maybe 52. And then you fill gravel in around the edges. And the whole point of a large diameter well is to be a storage vessel. Water seeps in slowly. There's typically not enough water available. Most of this is fine textured material, which water can move through slowly, but that's it. So you have enough storage that when you use the water in the morning or in the evening, it lowers the water level in the well, and then it sits overnight or during the day when everybody's gone, and it fills back up. And so the reason you have it 3-foot diameter or sometimes larger is just because it's like a cistern. It's meant to store water that seeps in slowly from our surrounding areas. So the other design on the right is where there's it looks like a drilled well at the top. It's got a regular well casing. In this case, they've got a pitless adapter, and this is an area where it'd be freezing. And then there's a concrete pad at 10 feet or lower, where then it's still the same large diameter well where water can seep in. It's just done in a way that you put clean earth fill in the upper 10 feet above that concrete pad, so that there's less chance of surface material seeping down and getting in the well. Okay, sand and gravel wells. So a sand and gravel well is finished in a sand and gravel aquifer, which, so that's why you have a well screen, which this little picture here is a stainless steel well screen. So the screen lets the water in but keeps the sand out, okay? And so here's a diagram of what that looks like. Usually you have a well pump that's in the well, and water seeping in from the sand. And when you start pumping this, the water level will drop in the well, and then water from the surrounding area, because it's at a higher level, it's going to flow towards the lower level, like I mentioned earlier, and try to fill that back in. So because of the porosity of sand and gravel, it keeps filling in the well. And so a lot of times you see in a lot of irrigation systems along river bottoms or in sandy areas, they're pumping 12 or 1,500 gallons a minute. And so a lot of times the sand and gravel aquifer is very prolific. The screen can be stainless steel or PVC. And as far as the screen size, what usually happens by screen size, I mean the slots between each woven strand of stainless steel there is sized based on the sand grains that you find when you drill. So you drill this well, you catch the cuttings as the material comes up, and you determine how coarse or fine the sand is, and you size the screen appropriately so that it keeps the sand out but lets the water in. If you're in a coarse gravel, you can have bigger slots. If you're in finer sand, they've got to be very narrow slots. And there are cases, there's there's a place not too far from here where there's an aquifer that the sand is so fine that no matter what size slot you use, a little bit of it's getting in the well, and then your pump will start pumping sand, and that's bad because sand is such a scouring material that it'll ruin your pump faster, or even can scour your pipes and eventually cause pitting in those as well. Here's a typical well log for a sand and gravel well. This is an Illinois log, which is what I use usually, but you can see on the bottom right is the formations it passed through: topsoil, yellow gravelly clay. There was some sand, just 1 foot of sand from 69 to 70. That's not enough for an aquifer or for a water supply. So they went a little further, and at 204 feet, they hit 26 feet of fine sand, and then more coarse sand that was salt and pepper. It just means the grain, there was some black grains in there, 10 more feet. So above that, the casing and liner and slot size for the screen, they put in, they're saying the water's coming from the sand from 230 to 240, so the thicker or the coarser sand. They put in an 8-foot length of 12 and 14 slot screen, and above that is 4-inch diameter, 11-pound drive steel casing from 0 to 230. So that's your well information. It also has on the below that 16 and 17 where the static level was 75.5 feet below the top of the well, which means water's coming up above the top of the aquifer, so this is under artesian pressure. They didn't take a pumping level measurement. I'm not sure why, but they pumped it at 15 gallons a minute for an hour, and it was fine. Typically what a driller will do is, if they're going to put, say for a typical home, you might have a 3 or 5 GPM pump, and so they'll pump it much harder than that. So they put in a 15 GPM pump here, gallons per minute, and they pumped it. So if it's pumps 15 gallons a minute for an hour, then a 5 gallon per minute pump or a 3 gallon per minute pump is probably not going to have any issues. And so, but typically they would measure the pumping level as well. You know, it might say the static level is 75.5 feet, and if they measured the pumping level after been pumping for an hour, it might be at 85, or it could be at 120, or who knows. So in the end, they set the pump on the, if you look at number 5 on the left, they did put in a 15 gallon per minute pump here, which is unusual. They must have livestock, otherwise you wouldn't do that. They set the pump at 175 feet. So since the water, that's 100 feet into the water, likely not gonna be a problem. Oh, and here's a remark at the bottom, I missed that. So they don't have the drawdown because they developed it with air. So they run an air hose down basically and push water up. And then as they push the water up, more water comes in from the formation, and that was to develop the well and get all the mud from drilling out of the formation and things like that. Okay, so bedrock wells. So the difference is you don't have a screen typically, and the bedrock acts as part of the casing. So when you drill a bedrock well, like in this example, in this picture, there's saturated overburden in a water table, and then everything above is called overburden. That's all the unconsolidated material, whether that's clay or sand or a mixture. It's probably a mixture more with clay and silt. That's what I meant to say. And then you hit bedrock. So typically you put steel casing 10 to 20 feet into the bedrock, and that's as deep as you go. So the well goes from land surface down 20 feet into bedrock, let's say, and everything below that is just an open hole. So when you drill into bedrock, most bedrock's solid enough that it acts as the casing. You're just drilling a hole through a piece of rock, and it won't collapse typically, and it acts as the opening for those fractures. And the idea here is if you don't hit any fractures, you won't have any water. So in this example, we show a kind of a major fracture that intersects the well, and so that's where their water's coming from. So there's a couple things that are of note about this. One, you could have a 600-foot well that only has, now most states require at least 50 feet of casing, but they didn't used to. you could have 25 feet of casing here, and then the rest of it's an open borehole. So if you encounter a fracture at 35 feet, then that water is going to get into the well, and even all the way down to 600 feet. But because the water is coming from these small fractures, that acts almost like pipe flow, so it's not really as extensive, and so water could be coming from further away, which is the bottom bullet there, can be influenced over a large distance, and depending on the situation at the surface, some of those fractures may run up close to the surface and actually be influenced by surface contamination. And so a bedrock well, especially where the bedrock is close to the surface, I know we ran into this in upstate New York. There were a bunch of wells that basically bedrock was at land surface, and many of them only had 30 or 40 feet of casing. They were 400 or 500 foot wells, but they were all contaminated. And part of that was because the septic systems were also sitting on top of that same rock, and it was not protected, and it was getting into the aquifer. So it's just something to understand. A 600 foot well doesn't mean your water's coming from 600 feet in a bedrock well. We're in a sand and gravel well, the same 600 foot well, water's only coming in the screen at the bottom. And so it's cased the entire way, and it has a screen that lets water in. So where a 600 foot sand and gravel well is just getting water from down at 600 feet, usually it's a 4 to 8 foot casing, maybe 10 feet if it's a private well. In a bedrock well, you could be getting water over almost the entire length of your well if the casing doesn't go very far. And so understanding where your casing goes to, how deep it goes to is really an important thing. And here's a bedrock well. You can see that if we look at the formation again, they had clay and a little bit of sand, and then broken limestone at 189, and then 68 feet of limestone. And then they hit shale. So they basically stopped. They went 3 feet into shale and stopped. Well, if you look at 15, they used 179 feet of PVC and then 20 feet of black steel. And they put the black steel at the bottom 10 feet into the bedrock. So the bedrock again started at 189. So they went 10 feet into the rock and seeded that steel casing and then put PVC on top of it. And that's because PVC is easier to break, and when you're seeding it in the rock, you have to use some force to make it solid, and so that's a typical way to save some money for the well owner, is PVC is cheaper than steel is the bottom line. But you can see here then that the static level was 130 feet. When they pumped it at 25 gallons a minute for 2 hours, it dropped to 160 feet. Still plenty of water, right? In fact, they put in if you look at number 5 over here, in the end, they put in a 12 gallon per minute pump, and they only set it at 160 because again, if you're pumping it half as hard, the drawdown is going to be less, and so it shouldn't be an issue. Yeah, a lot of good stuff on a well log if you have them. And that's the other problem we have, is that Illinois started requiring logs and licensing drillers and all those things in 1968. New York didn't start doing at least the log requirement until 2000. One other state, I think Mississippi, doesn't require you to file a log if it's less than 5-inch diameter casing. So we don't see a lot of private well logs there because a lot of them are 4-inch or 5. In other states, we're in the 80s or 90s. So the information available from each state is different, and you may or may not have a well log. I know in Illinois, I've worked my whole career, even though we were early in the game, if you will, and requiring logs and all those things, we still probably have about half of the well logs of wells that are actually being used in the state. We have 450,000 logs or so in our files that are active wells, and there's probably close to 800,000 private wells in use in Illinois. Okay, so there's lots of issues. That comes down to, though, really these things: public health protection, that's first and foremost, as well as source water protection, which means protecting the aquifer and the water supply that you're using, and then understanding the water quality of the water that you are using, whether that's a health concern or an aesthetic concern. Those are the things we really need to be concerned about. There are tons of issues like drought, flooding, contamination, all those things, PFAS today that are, in the news. And when those things happen, we tend to get more emails and requests and questions from well owners. Even the bottom one here, boil orders. So when a community issues a boil order, it's typically because they've had a break in one of their water mains. And so because it's not a closed system anymore and things can get in that water main if it's been broken, they have to issue a boil order until they get it fixed and can ensure that they've chlorinated the lines and all those sorts of things. When people hear that there's a boil order for a community, some well owners will even call the community and say, do I need to be worried about my well? It actually has nothing to do with their well, but some folks just don't get what a boil order is really for, and so they assume that it could mean that the same aquifer they're using could be part of the problem, and it's not. So, those things are a moment, though, for all of us. If we get a call from someone, it's a teaching moment where we can explain more about it, explain other opportunities like our private well class, or if you have information of your own to provide to a well owner, and I'm talking to the professionals that are in our group here, it's a chance to at least explain all that information. So, and this picture, it's a well that's halfway between Champaign and Lincoln, where my mom lives. They put in a confinement hog farm here along, and these trees are along a ditch or a small creek to protect the well from flooding, because if a well gets overtopped, then it's likely that well will get contaminated. They've just they just run the casing 10 feet above land surface, above the 100-year floodplain. A novel idea. It's a little hard to work on that way, but they're ensuring that if it does flood, that their well won't be overtopped, and they'll have to then take it offline and treat it and make sure that it's safe to use. So all those issues in the news they all come and go, right? Regarding PFAS, I don't think that's going to go for quite a number of years, but eventually we'll work it out, right? The EPA and the states will figure out more. We learn more every day about PFAS and how to treat it and all those things. But what I see, the two biggest problems we have with private wells are poor well construction. So when a state passes a well construction code or updates their well construction code, existing wells are grandfathered in. They don't have to meet the new code. They don't have to change anything. And so we still see a lot of these old dug and bored wells in pits, wells with piston pumps, all kinds of things that aren't necessarily safe. And as long as the well still works, a lot of folks are going to use their well, because putting a new well in is pretty expensive. And so we have that issue, which those old wells tend to be the ones where we have the most issues. It's also that a lot of folks who are on private wells just don't have the knowledge or education on how to be a well owner. And so we see a lot of people who they'll call a community when there's a boil order. I've had a number of community water operators tell me they've had well owners call them thinking they were on city water and not realizing they had a well in their front yard. And that's happened literally a bunch of times. And so becoming more knowledgeable about your well and knowing the basics is really critical to making sure you're keeping your water safe for your family. And that's kind of the message, I guess, today. As far as old construction, if you can, you should correct it. Again, well construction codes have changed significantly in the past 30 plus years, but every existing well is grandfathered in. We still see wells in pits. We still see hand dug wells. The well I grew up on, my grandpa hand dug in 1933. It's only 14 feet deep. It's at the bottom of a ravine where water can run towards it from three sides, and it's in a pasture. It was never safe. My body got used to that water when I came to college, started drinking city water that was chlorinated. I went home at Christmas. Our well water made me sick. And you just don't realize those things, but they're not safe. So not only are they a chance for contamination and from the surface, but they're also a safety hazard. The picture on the left is from the Washington State Department of Ecology. They had a blog for a while, and in Washington State, it's the Washington State Department of Ecology that licenses drillers, that manages the well construction code, and all things related to private wells as far as a state agency. And so they had a blog for a while, which I followed, and this is a picture they put in there. There's just a big piece of plywood over this well. You can see the corrugated pipe, the little blue pump at the surface, and the woman stepped on that, and she fell to her death. Now, this little well house, you can see all the gray stuff on the ground. That's probably rotting insulation or insulation that mice have got into. There's a little funnel there that was probably for oil for the pump. Excuse me. Just not a safe situation to have that piece of plywood as the only thing between rats, mice, snakes, whatever that might fall into that well. And as I'm getting over bronchitis, so if I need to stop and take a drink, I'm going to have to do that the rest of the way, and I apologize. The picture on the right, that is a dead goat. So there, if you look close enough down at the bottom, there it was old stones in an old stone well, and they put a piece of concrete pipe over top of it and pushed it down over the top. But that only sticks up out of the ground maybe a foot, and it wasn't covered. So somebody's goat got out, saw there was a water supply there, fell in there. And in this case, this well wasn't in use anymore. But we've even had folks on our webinars who've said, hey, you know, my dad's water tasted funny when we visited. So we looked in the well and there were a bunch of snakes, or there was a dead rat, or you name it. It happens a lot because the wells aren't properly protected at the surface. No, excuse me. One second. Okay. So what should you do with these wells? Bring them up to code if you can. You can find out what the code is from your local health district or county health department, or it should be online if you're with your state agency. If they have a statewide code, you know, every state has well construction code but two, Pennsylvania and Alaska, and Alaska's state agencies are all working together. They have a work group. They're trying to change that. But even so, if you don't have a jurisdiction that has recommendations for best practices or a well code, use somebody else's. You know, every other state does, and it's just a safer thing to do. So, but if you can, if your well's in a pit, extend the pipe up to the surface, fill that in with clay grout or just or cement so that it can't water can't seep in. You know, if you have a well in a pit, which we ran into, I don't know, in 2011, I hired 4 geology students to inventory wells in 9 rural townships in a farming country of Illinois. They found 1,708 wells. We only had logs for like 750 of those, something like that. But we also found 40 wells that were still in pits. And I know 40 out of 1,700 isn't a lot, but that's still a lot of, in a 9 township area of 1 county, that's a lot of wells that are in a pit. And they've been that way since, you know, these are farm wells. They may have, a lot of them are probably now close to 100 years old. But you should fill those in. They're a safety hazard. Not fill in the well, but fill in the pit. Raise the pipe up to the surface. Use a pitless adapter if you need to. In Illinois, you can do because of freezing. And then, you know, talk to a well contractor or your county or even your extension about what to do to make that safer. So the same thing with abandoned wells. There's probably as many abandoned wells out there that aren't used, that need to be properly abandoned, as there are wells that are actually in use. So because well logs weren't required in most states till sometime in the 60s to 80s, there's a lot of old wells that we don't have on file. The well I grew up on, not in our records here. But like wells and pits, they're a safety hazard. People, if somebody walks on your property um, and falls in an old well, whether you knew it was there, but maybe the plywood that you had over top of it's 25 years old now, and so it was rotten. You might be responsible, or you would be responsible if they get hurt or get killed. Or if you have an old well where people, the other thing people do is they'll dump stuff down in it. It's a nice hole in the ground that you can, out of sight, out of mind. Well, if it contaminates an aquifer, you could be responsible. And so this happens more than you think. Both of these pictures, again, are from the Washington State Department of Ecology. And one, they're pulling a horse out of an old well. Katie Sue was trapped in a well. And the other one, this guy didn't know he had a well. The Sheldon man falls 45 feet into a well. He was in his backyard, fell into the well 45 feet. They pulled him out and he walked away. Very fortunate gentleman. And these newspaper clippings are all from the 90s, where 3 of those are from Illinois, and the third one down is Jessica McClure. If you remember, it was covered live on CNN back in the 90s when she fell into a well. It took them 22 hours or something like that to get her out, and it was covered live on TV. It brought a national attention to the issue of these old abandoned wells that aren't sealed. And so if you have one, it's worth it to get it properly sealed so that it's not a risk to you or anybody else. Or you see where people get tractor stuck, the tire gets stuck, or a lot of things happen with these old wells. Okay, so we're going to talk a little bit about the difference between aquifers and aquatards and some of those things in water flow. So an aquifer is a saturated bed formation or group of geologic formation that yields sufficient quantity of water. In my field, they argue about what an aquifer actually is or isn't. So if you have a very thin aquifer that you can maybe get 5 to 10 gallons a minute out of, that's an aquifer for a private well owner. But for a community that needs a 200 or 400 gallon per minute well, that wouldn't be an aquifer for them. And so how you want to define that is really up to you, but it's basically a unit that provides water of a sufficient quantity. That versus an aquatard, which doesn't yield sufficient quantities of water, like our silt, clay, or shale. And it also doesn't let appreciable leakage through, meaning it retards the flow of water. And again, different users and uses will define what an aquifer is or isn't. And that's kind of the scientific definition. It's not a big deal as far as how you might look at it on your property. But geology is different everywhere. You're not guaranteed water just because you put in a well. And so it's good to know what you might have available. And if you really want to learn about the geology of your area, your state geological survey is probably the place to go. Or in Illinois, it could be either our geological survey or water survey. And I know from our own efforts, if someone calls us, we're more than open to trying to help them understand where they're at, what data we might have available, all those sorts of things. So confined versus unconfined. So an unconfined aquifer is where the groundwater has a free surface. So if we look at a jar of sand and we put water in just halfway up the sand, so the top part of the sand is still not saturated, but there's a line where the water becomes saturated, that's the water table. And the same thing happens in the ground. If you, in some areas, you may dig, say you're digging a foundation, you may have to get a contractor's pump and keep the water pumped out of it because the water table is really shallow. And even though it's not sandy material, it's still saturated. So water, when it infiltrates, reaches a point where it's saturated. That's the water table. That's not necessarily in a sand and gravel aquifer. The water table is the top of the aquifer. It's unconfined because it's got a free surface, which means it's atmospheric pressure. Where in a confined aquifer, like the ones that I showed you today, is where the water level rises above the top of the aquifer, and there's a unit above that that keeps it under pressure. So when you have an aquifer that starts at 200 feet below land surface, or like in our bedrock bedrock example, the bedrock started at 189, and above that was clay, and the water level in the well went up to 75 feet below land surface. So it went up another 110 feet. That's the pressure, and it's confined. So it's under higher than atmospheric pressure, and that's called artesian. Hopefully that makes sense. So we have here is this is the water table. There's an unconfined aquifer in the saturated zone, and there's bedrock below that. So if you have a confining layer, you have two different water level surfaces here. So see how the wells, the blue is different? In the unsaturated aquifer on top, the water level is the solid line, and in the deeper confined aquifer, the water level is the dashed line that's in the that comes up into the aquitard. Now, so what that means is, so that confining layer, that aquitard, that's a clay or a shale, whatever it might be, the water level above it is higher than below it. And so there's a net movement very slowly through the aquitard going down. But it's also possible to have this reversed, where the deeper aquifer has a higher water level than the shallow one. And then there's a net, water's trying to, because it's pressure, it's pushing up. It has more influence. And it moves very slowly. It's not, doesn't provide a lot of water, but it wants to be even. They want to be at the same level. And so that's what happens. So here's an aquifer that's confined. That's what the little dashed lines mean. And there's a separate water table that's up there. But where it's black there and the little triangle is the water level, you have, this is an artesian well because the water level's above the aquifer. So it's the whole aquifer is completely saturated, and it's got pressure on it. Think of it like if this was a big juice box and I squeezed it, water would come up the straw to a certain point. If I squeeze hard enough, it's going to come out the top, right? And so it can be below the water table, it can be above the water table, or it can be flowing. An interesting fact, Michigan has a really great handbook on flowing wells. It's called the Michigan Flowing Well Handbook. They were losing 28 million gallons of groundwater a day to flowing wells that weren't capped. So they passed a law in Michigan that every flowing well had to be capped. And that basically keeps the water from escaping on the ground. And by doing that, you create water pressure in your line before you even get it to your pressure tank. It's kind of interesting. So here's another example of how that all works. As I said before, bedrock and all the geology are not flat, right? There's a stream over here, there's uplands to the right. And so this confined aquifer, artesian aquifer, the second one, it ends up being at land surface somewhere away. This could be 100 miles from the stream, right? We actually have that situation in Illinois. West of Chicago, there's a recharge area for an aquifer that in the Chicago area is over 1,000 feet deep. And so the water comes in in the recharge area, it runs down, and so that's dictating what the water level is because it's trying to move towards lower water levels. You can see the dashed line going across for the two wells that are in the deeper aquifer here. One of them is the water level comes up to the dashed line. The other one, because of the land surface dropping so much, that well actually will flow because the head or the potentiometric surface, the water level, wants to be all the way up where that flat dashed line is, but it's lower there just because we don't have our well only goes to that high. And then the water table is totally a separate unconfined aquifer that has its own water level. It's different and it's connected to the stream. So this is very typical along any major river. You can have more than one confining layer that separate these aquifers, and because of that, the water levels can be different, and it can be whether it's artesian or it's flowing artesian. It just means it's under pressure. Here's the Chicago example. There's a St. Peter sandstone and an Ironton Galesville sandstone, and you can see the elevation here. The blue on this is Lake Michigan, and so the red line, the dashed red line, is where there is the water level in those two aquifers. And typically these are both open, and so they've both the Ironton Galesville and the St. Pete have similar water levels. But you can see because of pumpage in the middle, water's flowing both directions towards the center here, because wherever there's less pressure, water's trying to will go there to try to be even. Think about a bathtub. If you fill it up half full, it's a flat surface, right? And if you pull the plug, the drain, right where the drain is, you'll see swirling water and it's lower, but everything else is moving towards it because it's at a lower elevation. And that's what happens in an aquifer. When you pump water out of a well, you lower the water level right at the well, so everywhere surrounding it tries to fill in to make that flat again like it is in your bathtub. And so that's why this looks like it does. And the water's flowing both directions. Yeah. So it looks like it's flowing downhill, but it's flowing to a lower pressure, not, yeah. All right, so the other thing to understand about a well is the influence it has on the surrounding area. So these are idealized examples. We're assuming this is all sand and gravel, and it's all uniform sand, all the same size grain, same size in every direction, all 360 degrees. So if you had that situation when you pump a well, the drawdown would be just like this. It'd be radial. It'd be the same at 5 feet away in every direction. It's going to be 410 feet. So at the well, we've turned the pump on. It's dropped the water level from 460 down to 400. And the cone of depression is that area that's been dewatered. You can see at the top. The top is a side view. The bottom part is a top view. You're looking down at that's the elevation of the water. So at the well, it's 400 feet. As you move away from the well, the water level comes up, like you can see on the upper diagram. That curved line is the water level that's full. And because we've lowered the water level at the well, water's coming in all radial directions towards the well to fill it back in, trying to be level. And how fast water can move through the aquifer and how much water's in storage dictate how big this cone of depression will be. And so it might be very small. It might not draw down very much. We have an aquifer that's so extensive when we pumped it at 2 million gallons a minute, or no, got that wrong. It's 2 million gallons a day, which is about 1,400 gallons a minute. It only dropped the water level 2 feet. And so it's that good and that thick of an aquifer that water could get in and fill back in that fast. Whereas if it was a poorly sorted, not very extensive, you might see 60 feet of drawdown at the well, and it might extend over, half a mile, where in that other case, it was 2 feet of drawdown and we only saw it about 200 yards away from the actual well. So depending on how many wells you have, you can have overlapping cones of depression. And again, it's about the water that's available to run towards the well whenever you pump it. And so between the two wells, there's not as much water available. It's trying to go both ways. And so it lowers the water level more in that area. If there's a boundary, then there's not an extensive amount of water off to the left. So it's going to use more of it and there's going to be less available. And that's kind of what this is showing, because you're at the edge of an aquifer. And on the opposite side of that, if you have a river, it's at a set elevation and it's basically a continuous source of water. You're not going to lower the river by pumping a well if it's very large. And so it acts as a constant elevation, 445. It's always going to be there. And so if you have a well in that area, you're eventually going to be pulling more water from the river than from the other side, just because it's a steeper gradient, so water is moving faster from the river to the well. And so this is a concern for like a community water supply that's in a bottom ground around a river. They may have to treat it like it's surface water, because if it's coming from the river and there's not much distance between the well and the river, it can have all the bacteria and other things that surface water have, and it's considered groundwater under the influence of surface water, and they have to treat it like it's actually surface water even though they're pulling it from the ground. So, but that's the differences between different types of wells depending on how good your aquifer is, how extensive it is, what the water levels are, how permeable it is, and how porous it is. All that all ties together to give this sort of a what's going on. And you can see on the opposite side of the river here, those are parallel lines, the 460, 470. That's because the flow direction is perpendicular to the flow line. So where those lines are vertical, that means the flow is horizontal towards the river, because the aquifer is at a higher elevation than the river is. So this river is a discharge for the aquifer off on the right side of the river. So I want to show an Illinois example, but a number of states have these now. Our State Geological Survey and the Water Survey were sister divisions, if you will, of the Prairie Research Institute. And so we work together on a lot of things related to groundwater. They also do other things like oil and gas and coal and all those other things that we don't do. But they have an online system called, for better or worse, ILWater, Illinois Water Well Interactive Map. And it's a Esri product that you can show. You can look at all this stuff and see all the wells. So when you get into the site, you see the state of Illinois. As you zoom in, once you get to a certain scale, then all the wells show up. So these are the wells near Champaign, Urbana, which is where the University of Illinois is and where we are. And you can see right off the edge of the darker area is considered the aquifer in this area. And so you can add layers. So it's showing water and related wells, and it's showing aquifers, and then reference layers are the townships and ranges and some of those things, roads and town names. But all the blue dots are water wells. And so if I zoom in closer and I clicked on a well, there's actually 3 wells here, and I'm looking at the second of the 3, that's 269 here, by Willard Airport, which is just south of town, and it was drilled in 1959. This says it's 269 feet deep, and then there's an API number, which is the Geological Survey's number, and then the Water Survey also has a P number. Well, I looked at a different well, and I clicked on that blue number, and it gave me, this is one of the other wells there. This one's 244 feet deep, and this is a generated log from the Geological Survey. They've actually entered all this geology, and this will show up on their website. Now, if you go to a different log, some of them also have links to the scanned original well log, and that's the Water Survey's job. So we scan all the logs as they were originally written and have files of those. And this particular well, which is only 169 feet deep, it's at nearly the same location, has images available from the Water Survey, 3 different ones. So if I click on one of those blue boxes, then I get an image of the actual well log. And this was handwritten. The one I showed you before was typed, but this is from 1968. It's 169 feet deep. They put in a 5-foot concrete pit before they put in the well. I don't think that pit's there anymore, but just the same, you can see that they pumped it at 15 gallons a minute for 2 hours, and the water level dropped from 91.6 feet to 117.6 feet. And the aquifer is actually in that lower 25.5 feet, or the well is, from the formation they're using this to the 169. So there's a 7-foot screen that's 12 and 10 slot screen. We've went through that before. So that's what I have on groundwater and wells. I do want to talk a little bit about private well class before we get to our questions. So I mentioned earlier, it's a set of 10 lessons. They're self-paced. You go to privatewellclass.org, click on sign up for the class. It'll ask you for your email, your first name, and what state you live in. And so then you'll get an email once a week for 10 weeks with a PDF attached that goes through the 10 different lessons. So this is the front page, and take our free class, click on that. For each lesson, like the first lesson is called The Science of Groundwater, we link to other resources that might be beneficial. Each of the lessons is 6 to 10 pages long. I think it's, in the end, I want to say it's about 75 pages total for all 10 lessons. But then if there's other material or if something didn't resonate with you, you can go to and look at these other resources, and they're all from vetted agencies, or universities, and they contain a lot of good information on wells. I mentioned the Michigan Flowing Well Handbook. under lesson 2 that's described, and there's a link to it. And it's a great document. If you're in an area that has flowing wells, we only have a couple areas like that in Illinois. They're pretty small, but it's a great tool to understand the types of well caps you need and all those things to actually seal that and keep it from flowing. The webinar, like we're doing today, is recorded. Under webinars and events, there's a past webinars button. So this is one we did in October. And again, you can go through the whole thing's on YouTube. You can watch it full screen. Usually every July, we do a septic system webinar, Septic System 101. We had to do it in August this year, just the way things worked out. But we only do it once a year. It's really useful if you're concerned about your septic system and understanding. I know we have a septic question today or two. I'll answer later. And then one of the biggest things we find is, half the time the calls I get, not half, but there's a fair number of questions I get about, my pump failed or my well's not working. I don't have any money to fix it. There really aren't a lot of resources for well owners to fix their well. It's really on your own. Just that's the whole nature of being on a private well. But there are some funding and financing options, especially for lower income folks. And so we did a webinar on this. I think this was in 2020. We're actually one of the latest farm bill that was passed, I think in 2019 maybe, includes money for USDA to support well owners and for replacing or fixing wells and septic systems. And so we're doing this webinar again in February, and we're actually having USDA on the call to talk about some of those available resources. And again, typically those are reserved for folks with lower incomes, and so you have to meet certain criteria there. But yeah, there is some help. And then lead. So after Flint happened, everybody's worried about lead. Many rural homes are older. They all have lead pipes. And so we had an expert from Virginia Tech help us out with this webinar. And she went over some of the research she's done, what they found. And we provide resources on lead that homeowners need to know. Lead is not a well problem, typically. It's a premise plumbing problem. You can have areas where if they've used galvanized drop pipe or lead drop pipe, or there's a lot of, especially deeper wells, where it could be coming from those materials in your well, but it's not a naturally occurring thing. There's only a few areas in the country where you really have a lead issue based on the lead that's naturally occurring in the ground. And so this goes through all that. And yeah, if you just, again, go to webinars and events and click on past webinars, you can find this and all the other ones. And again, there's questions at the end and they're all worth seeing. We created a lead page. It's just privatewellclass.org/lead. And that's so that we tried to link to all the resources that are out there. There's some really great filters that you can put on your kitchen tap that'll remove lead at very high levels. And so all that information is here. I know the US EPA did a bunch of research on different filters for kitchen taps and found that they work really well. And so there's all that information is on that page. Again, it's just privatewellclass.org/lead. And then we also have training videos. We call them the 4 to 6 minutes long. They're on one topic. What do I need to know about my shared well, which is a bigger issue in the country than I realized when we started doing this program 10 years ago. What is a sand and gravel aquifer? What do I do after a flood or a fire? There's a number of these videos that are specific to one topic. And again, they're all 4 to 6 minutes long, and they kind of give you an idea of what you need to be concerned about. Why does my well keep losing pressure? So we have a very similar one that's, how does my pressure tank work? That's had over 400,000 hits since 2016. It tells us that there's not a lot of great information about pressure tanks out there, as well as that a lot of people have water pressure problems that are on private wells. Just understanding how your pressure switch works and how to change that, and some of those things are really useful information. And it may be, it was originally you may add an addition or added a story to your home, and going up to the second floor, you need to switch out some of those things and have a little more pressure to get it up to the second floor, stuff like that. We also do a podcast. We've done 2 seasons, and so there's 24 episodes. We're going to launch a third one probably in February. And we've interviewed some really interesting folks. Dr. Alan Wolf on the bottom there is the head of pediatrics at Boston Children's Hospital. He does a lot with private wells and children that have health issues related to private wells. And so, there's a variety of folks we've had on that either participate in some of our conferences or are working in the industry. And Margaret Martins is the head of the Water Systems Council. And so, yeah, there's a lot of neat information if you're into that and you listen to podcasts. The entire thing is available in Spanish. There's a Spanish website where you can take the entire class in Spanish. And so we're trying to provide all this information. And again, our goal is to give well owners, just direct information that helps them understand why their wells are important, why they need to care about it, and why they should understand how it works, and so that they can be prepared on how to protect themselves from any risk related to their well or water quality. And so, that's the point of the class. It's been pretty successful. We've had over 11,000 people take our class so far since we started this program, which is great. And hopefully we can reach a lot more. So the rest of our time, we're going to answer questions. Yeah, and we had, I want to say there's about 80 questions that we got from folks who registered. We obviously can't answer all of those, but I did pick some that either we haven't done before or they were asked by a number of people. Again, if you go back to our past webinars, you can even skip all the stuff I went through just now through the class stuff and go to the questions. Every month they'll be a little different. And so if you're interested in just learning more about different issues that people have and things like that, you can go through all of our webinars and see all the questions that have been asked. We've answered, literally hundreds of questions over the last 6 or 8 years. So I'm just going to go through the questions we've received that, we answered for today. So why is it that 2 wells not very far away from each other can differ so drastically in their flow rate? 15 GPM versus 3, and they're less than 500 feet apart. So, and they also mentioned topography. I summarized this because it was a much longer question. So topography is really irrelevant. It's about the geology and well construction and well depth. My first question to you would be, are the wells at the same depth? So they're in the same unit. And what do we know about the geology? Is it a bedrock well or are these sand and gravel wells? There's an irrigator up in Kankakee County in Illinois that I worked with. We did a big irrigation study back in the late 80s where he put in a 16-inch well that was 400 feet deep that only pumped 30 gallons a minute. He was trying to put in an irrigation well, but he missed every big fracture that was available. He moved over 200 feet, hit a large fracture, and he has an irrigation well that pumps over 1,200 gallons a minute. So it really depends on, where you drill matters. There can be a lot of variability. I'm going to assume these are bedrock wells to have that, but 15 to 3 isn't, it could just be a difference in one additional fracture that one of the well hits and the other one doesn't. If they're not bedrock wells, then I probably need a little more information. But if they're really identical wells in the same unit, then that's really probably what's going on. Is the quality of water better in deeper wells? And there were several questions about deeper wells, or people made comments about, someone told me that deeper wells are always better or they're better water quality. So we will talk about wells being deeper as being more favorable, and that's basically all other conditions being equal, a deeper source is better protected from the surface. So as I explained though in the bedrock example, having a deeper well doesn't mean anything if you only have 40 feet to 20 feet of casing. 2 wells that are 200 feet deep could be very different if one's sand and gravel and all the water's coming in from 195 to 200 feet below land surface where the screen is, versus the bedrock well that's 200 feet deep, where it can come in from 30 feet at the edge of where the casing stops down to 200. So it really matters about the geology and the well type, how much casing there is, all that sort of stuff. It doesn't necessarily mean the quality of the water is better either, because you can have natural occurring contaminants in deep aquifers like arsenic, uranium, radon, that you might not have in an unconfined shallower aquifer. So, you know, it's not always the case. It's just a matter of, it does help. In theory, a deeper well would be further away from surface contamination. And so that's kind of where that comes from. Yeah, and you also need to know if the well is properly constructed or grouted. And yeah, so I think I've answered that. Okay, so a developer will be digging and changing grading 20 feet from our wellhead. Should we be concerned about this causing structural water quality problems? Yeah, I'm really not sure about the structural problems. You know, it's not likely, unless they're going to be, you know, if it's rock and they're going to be dynamiting or something like that, then there'd be maybe some issues to worry about. But even if there's a lot of vibration, it could cause water quality changes. And so, you know, as an example, an extreme example, we had a monitoring well in Southern Illinois that there was a small earthquake down in Missouri, and it changed the water level in our well by 4 feet. And it just basically, whatever changed between all the connections and the fractures in the rock, it lowered our well 4 feet, and it stayed that way. And so how that changed the water chemistry, it could have. This isn't a well we monitor for water quality, but if it's a different water source, or there's a different percentage of water coming from different fractures, it could change the chemistry just because of the natural rock material and what it's made up of. And so the best thing we think you should do is go ahead and take a water sample for inorganics and metals before they do any work, and then do a follow-up one a few weeks later. And you could also see some cloudy water. We've seen where, you know, folks near a quarry where they've dynamited may have cloudy water for a few days. It doesn't necessarily mean there's going to be any changes in water quality. It could have just disturbed something so now you're pulling water that's, yeah, you know, had some unconsolidated soil that's got mixed up in it and dissolved, and so it's causing some cloudiness. But again, testing is really the best way to determine that. So we've had a number of questions about treatment. Someone asked about UV, someone asked about you know, hardness and nitrate, several others. And so a few years ago, Minnesota Department of Health put together this guide called Home Water Treatment. And Katie, maybe you can put this in the chat, this link, but even if not, you can Google it and find it. But it's really an awesome summary of everything you want to ask about basic treatment based on what constituents and what kind of treatment you're looking at. So it's called Home Water Treatment from the Minnesota Department of Health. And if you just Google MN for Minnesota Home Water Treatment, it should come up. It'll come to a page, and then you can download the PDF. But it goes step by step on why you're doing this. It talks about, if you're going to have treatment, you should have one that has these 3 labels: NSF, the National Sanitation Foundation, the gold seal from the Water Quality Association, or the certified UL water quality symbol. And so those are third-party certifiers, and it means that whatever company made this treatment device had NSF, WQA, or UL test it and prove that it removes the constituents it's listed as removing. So if it's an arsenic device, if it's got those symbols on it, they're verifying that this treatment equipment will actually remove so much arsenic based on their standards that they tested it at. I would not buy a treatment device that doesn't have one of those 3 symbols. It might be more expensive because the companies have to pay to have that extra work done, but it ensures that you're getting a device that's going to work, and it's guaranteed to do that. And it gives you some leg room, basically, if there's any problems. But as you go through this document, it lists all the constituents on the left going down in rows, and the columns are the type of different kinds of treatment that'll treat it. So for instance, for hydrogen sulfide, there's a number: aeration, continuous chlorination and filtration. And so then further down, it explains what each of those processes are, how much, even what the pros and cons are, if it takes a lot of water, if it does, if you have to add stuff, the costs, initial, it's point of use or point of entry. One comment I'll make about point of use versus point of entry, be sure that there's a really good reason to need a point of entry treatment device. So point of use means right where you're using the water. So that would be like a lead filter on a kitchen tap or an RO unit under your kitchen sink. Point of entry means where it enters your house. So you're treating every drop of water that comes into your home, for your toilet, for your shower, for your dishwasher. There are very few contaminants where you'd need point of entry. I've run across in the Northeast where folks have been sold a point of entry arsenic treatment device. There is no reason to have a point of entry treatment device for arsenic if you need to treat the water you're drinking and cooking with. It won't hurt you in the shower. It has to be really high, more than you typically see in groundwater. If it is really high, in the thousands, then maybe ask a health professional if it's a risk dermally or whatever. But we talked to Minnesota Department of Health, and they agreed that like for arsenic, you don't need a point of entry device. It's just a lot of extra money and a lot of wasted water. So that's the one thing I'll say there. So yeah, it goes through this, carbon filters are great for taste and hydrogen sulfide and things like that. RO down at the bottom, RO is a membrane. Any particle is larger than a certain size won't go through it. And so it removes a lot of things, including nitrate. I know one of the questions was, what's the best way to remove nitrate? RO is a good way to do that. So anyway, it's a really great, well-developed document that should get most people on their way. And it's also good if someone comes to your house and let me go back, and they do a pH test and say, oh, your pH is this or whatever, you really need this, this, and this. You can go look at this document and go, well, why would I need an RO unit if it's just for that? It prevents you from being sold something you don't need. I've ran into more than one well owner who I went to their house to do a well assessment, and they have $5,000 to $10,000 of treatment equipment in their basement. I'm like, oh, what was in your water? We've never tested. So they were worried about it, and someone came to their house selling treatment equipment, and so they went ahead and spent all that money, even though they'd never really tested to see what might be in their water. So do your due diligence. Most treatment professionals are reputable, but like in any profession, there are a few that aren't. And so, it's buyer beware. And if you have any questions related to that, I know the WQA has a program for training treatment professionals and setting standards and ethics standards and all that stuff. You can go on their website and find a treatment vendor near you that has went through that program, and it gives you at least some assurance that they're going to be more reputable in what they're doing. Okay, I had my well hooked up to my kitchen sink. After 5 minutes of running, it would stop. I'd wait 20 minutes and the water would run again. I thought there was a pump underground with the well. Why would it do this? So it isn't your pump, right? It's that your well doesn't have enough volume, or it's very slow to recharge into the well from the surrounding geologic unit. So it's, we had the same problem with the well I grew up on. It's only 14 foot deep. It was a dug and bored well. As I mentioned, if I put the hose in our horse tank where we watered cattle and horses and forgot about it, we might run out of water for 2 or 3 days. It took that long for it to recharge and to fill back in, because if it's finer material around the well, Water moves slowly through it, and so that's why I mentioned when you have a dug or bored well and it's shallow, that's why it stores and adds water during the night. It might fill back into wherever the water table is, and then you use it, it goes down and slowly fills back in over time. You're in a situation where you just don't have that much water available. There's one thing I forgot to mention here is if you know how deep your well is and where your pump's set, it's very possible that you could lower your pump. You don't want your pump near the bottom because it's going to stir up sediment and that'll come up through. But if you know, say your well's 40 feet deep and your pump's set at 15 or 20, you can probably lower it down to 30 or 35, and that might solve your problem. But when the pump breaks suction, it's just going to stop working, and then that's because the water level dropped below the intake for the pump, and then you just have to wait for it to fill back in, and it sounds like it'll do that over time. So it's just, like I said, it's like the examples for drawdown I showed earlier. How, depends on how quick water can come back in the well, how much you can pump and for how long. So, and there are places, I mentioned Pennsylvania and Colorado here, where they're low yielding wells. So in Pennsylvania, when all the fracking stuff was going on there, they have their bedrock is fairly tight, if you will, doesn't have a lot of fractures. And so there are a number of wells that were near a fracking site where when they turned on their water and the pump kicked on, the water level in the well, these are like 300-foot deep wells, it dropped 150 feet. And so, you had to have your pump pretty low. A lot of them have 2 gallon per minute pumps, things like that, so that they wouldn't go dry, if you will, because a lot of times those pumps are cooled by the water in the well. So if you get it too low and the pump stays on, you could burn up your pump and those sorts of things. And in Colorado, there's a gentleman who has a cabin on the western slope of the Rocky Mountains, and it's in granite. He's got, I want to say it's an 800-foot deep well, and it only pumps 0.5 gallon a minute. So he's got a very low yielding pump, and he pumps it continuously into a cistern. And so, I think he's pumping 0.5 gallon a minute or so, or less than that, maybe 1/3 gallon a minute, 24/7. And so it fills up his cistern, and he's got another pump in that to go into his house. And so when he's not there, and when during the night when they're sleeping, it's filling that cistern up slowly so that they'll have a volume of water available to take showers and cook with and do all those things. And so to know exactly what your situation is, I probably need more information. But it's likely one of those issues. Sandpoint wells. What is the life expectancy for a sandpoint well? Well, to me, it's really not about life expectancy. It's about whether a sandpoint can provide a safe water supply. A number of states don't allow them anymore. In Illinois, there are sandpoints, but they've changed the law. It says that you can install your own well in Illinois. You don't have to use a well contractor, but it still has to meet our construction code, and sandpoints don't. They're risky because they're typically in areas where there's a shallow water table and it's sandy, so there's plenty of water available. But because it's sandy, you also have a lot of surface infiltration. So every time it rains, every time any kind of spill, anything liquid is going to run right down into the water table where you're pumping your water. So typically when we sample a sandpoint, it's contaminated either with nitrate or possibly bacteria, and they're just not a safe water supply. There's no grout, there's no gravel pack. They're getting water typically from less than 20 feet below land surface, and it's just not a safe water supply. So it's up to you. It's certainly cheaper. You can buy them at a hardware store, install them yourself with a sledgehammer, get all that. But if it's going to be the drinking water supply for your family, they're just it's not worth it. Your water supply should need more than that. And, people will spend $60 a month for water service so they can have a sandpoint well. But if you just put a well in, like we have a county here in Illinois, Mason County, where it's sand at the surface and it's about 100 feet thick. And there's a lot of sandpoints out there. What I tell folks when they ask me, my advice is drill a well where the screen's right above the bedrock, right at 100 feet. Sand is a natural filter. By having it at the bottom, anything from the surface has got to work its way through all of that material, and that's the best water supply for that aquifer, is down at the bottom, and not have just a 25-foot well or 20-foot well, where everything from the surface, if there's livestock nearby, or if there's any kind of crops or anything, all that stuff is gonna make it to the water table. Well basics. Somebody asked, how do wells work? So going back to the fact that we have these video lessons and we have a class, that's just a general question. You really need to take our class to understand that. You'll have a much better idea. There's a lot to go through with a question like that we don't have time for today. But if you're willing to do the work, you can certainly find out a lot more about that and how wells work. Excuse me. Several people ask about pitless adapters, what they are, how they work. I showed them on the two diagrams with the bedrock well and the sand and gravel well. Basically, the key point here is the dashed line says frost line. So before the advent of the pitless adapter, wells were put in pits so that in the winter, the line wouldn't freeze. Because of the frost line. So, in Illinois, we may have, in a really hard winter, we may have a frost line down to 3 feet. So you need to have your discharge line from your well going into your house below that, or the pipe will freeze. So it used to be you ran your pipe out of the top of the well. Well, if your well is at the surface, then it came out of the surface and then went back down in the ground, that portion of the pipe would freeze and your well wouldn't work. So they developed the pitless adapter that's on the right. It actually just lifts out and lifts back in. It snaps in place and it connects the vertical pipe from your drop pipe coming up with the discharge line going into your house down below the frost line. But it's still your casing. You can see that's still the same steel casing or whatever, PVC casing, whatever it might be, and it just sits in place there and it's locked in place. But then you have a piece of pipe that you can just pull that out and then pull your pump out, and you don't have to mess with your discharge line. And this doesn't show a break like at the edge of the casing, but there is. So that whole unit comes out and then fits back in place when you drop it back in place. And so it's a way to get your pump out and to, it basically creates that elbow for you that's movable. And so you don't have to run your water line up above the ground. And so in areas like, Arizona or California, Southern California, you might have your pressure tank outside next to your well, and all the lines come up to the surface because you don't have to worry about freezing. But I just saw, there's several well owner networks that states have. So Texas, the Texas Well Owner Network is ran by Texas Engineering and Extension Service. They just put out their newsletter, it might have been earlier this week, where they talked about winterizing their wells because, if you remember last year, they had freezing weather down there that took out a bunch of community water systems and private wells and everything else and electricity because they're not used to it and don't typically have it. So they put out a thing with a bunch of advice for people who aren't used to that because, as a good example, my well that I grew up on was in a little well house, but if we lost power, which we were in a very rural area, and like the ice storm in 1976 when I was a kid, we didn't have power for 7 days. And so we kept a propane tank down there full with a heater on it so that if our power went out, we could go down and turn that on and keep that little room warm so that our pipes didn't freeze, because they did come out of the top of the well. And, if you've ever dealt with frozen pipes that burst, you're basically done until you fix all of that. And, in the middle of winter, when it's 2 degrees outside and it's the middle of the night, it's not the time to deal with any of that. So pitless adapter is a great thing. It keeps us from having pits, which, having a well in a pit means you cut it off and have the cap 3 or 4 feet below land surface. Anytime there's a huge rainstorm, that pit can flood, water can overtop the well. Snakes get in it, other kinds of critters might live in that pit. So then when you do have an event that overtops the well and water gets in, it's likely contaminated. So hopefully that explains things. And this diagram is actually in our class lessons. I pulled it from that. So that's why I keep saying, really, to learn as much as you can about your well, the first thing to do is take our class. I work for a local health department. I've been seeing well drillers not grouting the entire annular space on their well logs, which is a violation of our regs. Can you go over the health concerns that can happen from improper grouting? Well, certainly improper grouting is a bad thing. So, when you drill a well, say you drill a hole that's 8 inches and you put in a 5-inch casing. So the area between the outside of the hole and the outside of the well casing is called the annulus. And you put grout in there, which is an impermeable material, clay or cement or a slurry or clay pellets sometimes, that's used to seal that so that water can't run down the outside of your well casing, down the hole that you drilled and get to your well, into your water. And so, and that's called the annulus, that area. And so, so what I said here, you may not agree with, but your code is your code. A lot of places don't require continuous grouting over the entire interval of your well. But if you need to have a fully grouted annulus, it's really dependent on the geology, how much of a risk that is. Nebraska, I think I included this as the next slide, but in some areas, if you're grouting where the aquitard is, then you can use gravel where the aquifer is, and it's, it can't get through that aquitard. And so different jurisdictions do things a different way. But as far as talking about improper grouting, if you don't have grout in the right place or enough of it, then you run the risk of water running down the annulus and getting into your well or getting into the aquifer from the surface. And that's the whole point of a proper well construction, is that nothing from the surface can get in your well. And that's why you need to have a good cap, and you need to be grouted and all those things. I'm included another slide here from the past. And I had this in the last time we did this webinar in May, but someone asked which is better, cement grout or chip seal. So I told them then, the first consideration is your code. You have to follow what's in the code. As a driller or someone who inspects wells, you've got to do whatever your code says. But I recommend you take a look at the Nebraska grout study if you Google that. So the Department of Health and Human Services in Nebraska worked with Baroid, which makes grout, and they did the study in the early 2000s where they used pipe that was clear so they could camera it, and they used different kinds of grout and different kinds of geologies, and in some of those cases the grout didn't stay in the formation. So a state or a jurisdiction that has a rule for a certain kind of slurry, which is, it's liquid, you're pumping it in with a Tremy pipe, in some geologies that grout will go out in the formation and not stay in place. And so in the end, even though they followed the code, the well's not safe. And so it was really interesting when we found this stuff. So I had him come talk at our conference. We put on a private well conference in 2017, and he gave a talk on this, but you can look up their information. Nebraska really thought most states would change their well code after they did this study. No one but Nebraska has changed their well code because of it. And it's really something that states need to consider. I know I talked to someone in New Mexico who said they were looking at changing their regs because of that, but they haven't done it, at least as of last year. And, it's hard to change regulations, especially at the state level. Your state legislature has to do it. But I'd take a look, because even following state code doesn't necessarily mean, it usually does. I don't want to alarm anybody, but there are certain cases and certain types of geology where when you're using liquid grout, it's not actually staying in the annulus like it's supposed to. Okay, backwashing calcite filter. So how often should a system backwash, assuming calcite is a medium? So people use calcite filters to raise pH of the water when it's naturally low. So if you have a pH that's 5 or 6, or you can use a calcite filter to get that up, and that's important for corrosion. So community water supplies put in polyphosphates to raise the pH of their water if it's low, so that you don't have corrosion of lead or copper from lead solder, lead pipes, or copper pipes. So backwashing is how you clean that filter out after it starts getting full. You run water the opposite direction, that sort of thing. The best advice I can give you is find out who manufactured your filter, find their website, and find what information you need, because it's all right here. And I just went to one company's website, and based on the tank size and the volume of calcite and all those things, it tells you what your backflow rate should be and how often and that stuff. But even I guess that's not on here as far as how often to backwash, but you need to ask the company that made your equipment. That's the best. And if you go to the Water Quality Association's website, you might be able to find the information for the equipment you have, the treatment equipment you have. They have a list of a lot of those things, and like the manuals, the instruction manuals, and all those things in case you don't have that. But my advice would be to contact the manufacturer. So there are a number of questions like well water treatment information. I gave you some by the home treatment document. Site selection for well, basic well 101 info, what affects groundwater contamination, pros and cons of starting a well construction, I got that wrong there, on your property, and how do wells work. Really, those are all open-ended questions, right? You need to take our class. That's the best way to answer each of those. And just like for starting a well, if you're going to drill a well, we have a list of questions you should ask a driller, things you need to make sure in the contract. We have people who tell us, well, the well driller won't give me my well log. Well, you need to have it in the contract you sign with your driller that they're going to give you a copy of the well log, because and sometimes you're in areas where there's a lot of competition among drilling contractors, and so they guard that information as closely as they can. But you should always make sure you get a well log. I mean, so things like that are all in our lessons, and you really need to take the class and go through and read all the material. A couple more. What testing, if any, is conducted on groundwater on a site before a well can be placed? There's usually no testing in advance. You need, because you need a well to collect a water sample, right? And if there's not one already there, but there may be other information available. Talk to your state geological survey or a resource agency that deals with your private well agency. They can tell you what kind of aquifers are in the area, if there are other well logs. So like if you're in Illinois, you can look up the State Geological Survey's page that I showed you, and you can look at other well logs and see what's there. You can contact the water survey and find out if we have any water quality information for near you, things like that. And so your driller, nearby drillers, State Geological Survey, and state well record folks should be able to provide information on nearby wells, their depth, general water availability, and actually in some cases, like in our case, we'd have water quality information. We've sampled over 28,000 wells in Illinois over the last 50 years or so. But you could find that there's multiple aquifers with varying water quality because that happens. And so, so there isn't anything done in advance. But to be prepared before you do anything, you should find out all the information you can. Nearby wells are a great resource for that. When bacteria and/or elevated nitrates are detected in a well water, it's presumed it's a symptom of compromised well integrity. However, aside from identifying inadequate well cap or covers or obvious casing damage, which are all things that we've talked about in the past, is it worth further well or septic inspection and like a downhole camera, or preferable to treat filter the water? Well, one, I want to say this is an excellent informed question, because you've said a lot of things that we usually say on these webinars about if you, it's not presumed that the first problem is, well, I guess it is. It's presumed that it's a symptom of a compromised well integrity. So you can look and identify if there's a breach in the well near the surface, if the cap's not there, if it's an old well like some of the ones we showed pictures of, then clearly that's why you have bacteria in your well. But as far as camera in your well, you need to do your homework first. Are there any nearby sources? Is there a feedlot? How close is the septic system? And I'm assuming that disinfection didn't work, because a lot of times if there is bacteria in your well, we may not know why it got in there, but once you saw it chlorinated, it goes away and you can test regularly to find out, and it doesn't come back, then there's not a source. If it's a shallow, large diameter well or a sand point, those typically, are more likely to have that sort of thing. But as far as treatment versus a camera, most of the time, if you've tried chlorinating it or disinfecting and it didn't work, and you've done that a couple times, then really treatment is your solution. I'd only camera a well when nothing else makes sense and there's no clear reason that you can't come up with, and that's going to be a rarity. But if you have a specific situation, I'd be interested if you want to reach out. We had one of our RCAP folks said, these people have a well, it's in the middle of the yard, there's nothing around it, but they keep getting bacteria hits and they can't seem to shake it. They've disinfected a bunch of times, blah, blah. I just said, send me a picture. And in the end, there's nothing around it but 18-inch diameter tree, and it's a PVC casing. So what had happened in that case is as the tree grew, around the well is a path of less resistance than the native material. So roots had gotten around that and started squeezing that PVC until it cracked. And so, there's a lot of bacteria and bugs around tree roots. And so that was the source of their continual bacteria problem. And so there's always a reason if it keeps happening. It's just a matter of having a better idea of the site and what might be there. So, and this is, I think, the last slide. So I apologize, it's already 3. Finding mixed information about what I can, should, or shouldn't discharge into my septic. I get different advice and information from different people. And again, I summarize this because it was a whole slide long question in the end. So some states have laws on whether you can put backwash into a septic system. Like some states don't allow you to put softener backwash into it. So you should check that out first. But in general, what we tell people is your septic system works best if you put less into it so that the bacteria can work longer, they can grow better in the septic tank, and especially backwash. It depends on what the chemistry is. I know part of your question said something about doing an acid neutralizer or something. You don't want to put that in your septic tank where you're growing bacteria to get rid of your waste. So the bottom line is we suggest not adding any backwash, finding another way to discharge that. But we did, and I said August 2nd here, it was actually August 4th, our annual septic webinar. You should watch that. And if you scroll over, go on our webpage and scroll over webinars and events and then click on past webinars, you can scroll until you find that. But it's worth, all we talk about is septic systems for that 2 hours and answer questions related to it. So I think you'll get a lot of good information there, but we certainly recommend not putting backwash or, even your sump or your hot tub. None of that should go through your septic because it just doesn't give the bugs time to break things down when you're running that much water through it. And so I'm going to switch over to our questions. If I can figure that out here, and let me make this full page real quick and larger. Okay. On well survey 11 in the presentation, why don't they take a water sample? I need more context. I'm not sure what you're talking about here. Katie, do you have?
This individual was referencing earlier in the presentation when you were going through, I believe it was an assessment.
So one, the assessment's free. So the idea initially was to help folks understand their well better and give them advice and recommendations, but there wasn't funding in our program to provide sampling. Now that's changed. So RCAP does between 400 or so assessments every year around the country in total, and it includes a water sample. Each region does their own, so they use different labs. They may do a little bit different constituents, but you'd want to talk to one of the RCAP folks because they do take a water sample now and pay for it. But hopefully you understand if you're doing 400 well assessments, that's quite a chunk of change to pay for 400 water analyses that are, comprehensive as far as inorganics and metals. So that's why, I didn't, for the well assessments I've done, because I don't have any money to pay for that. It's not part of the program we have. I mean, their funding just doesn't cover everything we would like to do. Hopefully that answers your question. Where can we find local well records as well as local codes? Are they housed within state health departments? Well, it depends on your state. In Illinois, it's the Illinois Department of Public Health. It's a state agency, and there's a state well code, and that's where I would start. I would start with my state water well logs, and if you do that in Wisconsin, you're going to get DNR. In Missouri, you're going to get DNR. In Minnesota, you're going to get Department of Public Health. In New York, you're going to get Department of Public Health. In Washington, you're going to get Department of Ecology. So from there, you can find the folks who can give you that information. Some states have that on a nice interactive map like we do. Some don't. Some you have to request it. California for a long time didn't allow anyone to get a well log from a county health department but the person who owned the property. And now they've changed that, and all their records are open and available to anyone, which is the way it should be, and the way it is in Illinois. And so it's really variable, but your local health district or county health department should be able to tell you if they have well records or where you need to get them. That's where I'd start, one of those two places. So why drill a well deeper than where the pump is set? Also, if the pump setting depth isn't on a well log, is it assumed that it's at or near the bottom of the well depth? Usually you put the pump only as deep into the water as far as you need to know that it's not ever going to go dry. So for instance, in Champaign County where I live, if you have a 300-foot well into the Muhammad Aquifer, the water level might be 60 feet. It's a very prolific aquifer. It's 150 feet thick. It's sand and gravel. If I pump it at 10 gallons a minute, I might draw it down 2 feet. So there's no sense putting the well down at 300 feet when the water level is never going to go below 65, maybe, or if there's a lot of pumpage from nearby sources or the irrigation wells go in, it might go down to 100. So maybe I put it at 120 feet. But you never put your pump down in the bottom of a well because silt, sediment, sometimes a little sand gets in your well and it sits at the bottom, and you're stirring that up. So your water is going to be cloudy or have dissolved solids in it, or maybe actual solids in it. And your well screen is sized based on laminar flow into the well from the outside going through the gravel pack in the well screen. If you put your pump right down in the well screen, that would cause a much more higher velocity flow through the screen, and it could sort your gravel pack and let more fines and fine sand and those materials get in your well. So you never put your well pump down at the total bottom or because of sediment, or if you have a screen, it should always be 5 or 10 feet above your screen to prevent that gravel pack from being disrupted and potentially causing a place where finer material could get through your through your well screen. Hopefully that answers your question. Isn't it required to have a well driller sign and put their license number on the construction form submitted for monitoring wells? No. Well, I say no. Every state is different. It depends. If it's a private company doing an assessment for monitoring wells at a hazardous waste site or whatever, that's all handled by an agency that requires very stringent rules, even where they put the material that they've drilled because it could be contaminated. Yeah, it really depends on the situation and the state. Pennsylvania doesn't have well construction code and doesn't license drillers, so it depends on your jurisdiction. But I'd say, for instance, when we drill wells, we had our own rig, we had a licensed driller that we hired to run it, or if we contract that out, we're using a licensed driller. So yeah, but I think it depends on the situation. So you need to look at your state code and rules, because it's just different in every state. You know, when I say Pennsylvania doesn't license drillers, I had someone email me and complain, yes, we do. Well, if you go on Pennsylvania's webpage, every one of us on this call today could go to Pennsylvania's website, pay our $60, and get a certificate that says we're a licensed well driller. There's no testing. There's no continuing education credit. There's nothing that says that you're actually capable to drill a well. And it even says that on the webpage. So to me, Pennsylvania doesn't license drillers because there's no professional standard that they have to meet or any kind of testing to show that they have that capability. Okay. All right, I think that's what we have for today. Thank you for those that stuck around. If there's anything else, you can always email us at info@privatewellclass.org. Yeah, Katie, did I miss anything?
No, I think you're good, Steve.
Okay. Well, thank you, everybody. And we'll see you next year.